Welcome. This is, without a doubt, our final video for Chapter 7. Alright? Now, I'm making one more example of an optimization problem, and this is an optional video. You don't have to watch it, but nevertheless, I'm making one more for a couple reasons. One of those reasons being that I've only shown you optimization problems so far where you maximize the value, and you should see where you can minimize the value. And secondly, just with this type of problem, it helps to see several examples. You're going to be doing a lot of work on your own, so here's just one more example where you get the idea of how you optimize by finding critical values and then plugging them into the original function. Okay, read the problem. And you see that what we're dealing with here is an equilateral triangle and a square whose perimeters add up to 10. Now we're going to try to find out what the minimum total area of that equilateral triangle and square could be if we keep the perimeter at 10 the entire time. Alright, so the way this problem is set up then, the equilateral triangle could have any dimensions that we want it to, and the square could have any dimensions we want it to. So let's just say the length of each side of the triangle is x, and each side of the square is y. Alright, now one of the things we have to be able to do is come up with our function that's going to minimize the total area. Okay, we're looking for a minimum total area. So we need an equation then that calculates the total area for this equilateral triangle and for that square. Alright, now I need to give you the formula to find the area of an equilateral triangle. If you know the side length of an equilateral triangle and you're looking for its area, you can find that area by just multiplying the square root of 3 over 4 times that side length squared. Okay, that always finds the area of an equilateral triangle. And of course, the way you find the area of a square is you multiply its length by itself, or square the side length. So that equation will help you find the area. Now you know at this point that we want that equation to calculate the area in terms of one variable, not two different ones. So what you're going to need to be able to do is to rewrite this expression so that it only has x's or only has y's rather than both of those. I'm going to give you a little bit more help with that. If you don't feel you need it, pause the video now and work through this. If you do feel you need the help, watch this next little bit and then pause the video and try to finish the problem. And that last little bit of help is going to be involving the other piece of information that was given to us in the problem, that the perimeters, the sum of the perimeters is 10. Alright, well the perimeter of the triangle, hopefully is pretty clearly 3x since it is equilateral, and the perimeter of the square is 4y, and so you know that 3x plus 4y is equal to 10. Now you ought to be able to figure out what y is in terms of x, then use derivatives and whatever else is necessary to find the minimum total area. Alright, pause, see what you come up with. Here's a little bit of the work done for you so far. I calculated what y is in terms of x, and then I plugged that in to the area function right here. I just replaced the y with 2.5 minus 0.75x. And you might think you need to bother to square that difference. You don't need to, because what we need to do with that area function now is we need to find its derivative. And you've already done that. Let me just show you what it is. Okay, now whenever I was finding this derivative, the thing that you had to keep in mind is right here, you had to use the chain rule. So you can see how I multiplied by 2 and then reduced the exponent by 1. And then I found the derivative of the inner function, the negative 0.75, and multiplied that by the derivative of the outer function. Okay, then I decided to change things to decimals because I was going to have this term and this term that were both like terms, but it was going to be a little bit difficult to combine them if I didn't change things to decimals. Now that does make this an approximate value, so keep in mind that those range off a little bit, but not enough to be significant. Alright, so you end up with the derivative being 1.99x minus 3.75. Now, you know you need to set the derivative equal to 0, and again, hopefully you've done that already. And you should have found out that when the first derivative is equal to 0, the x is about 1.88 to 3 significant figures. That was your critical value. Now I want to take a look at the graph of this area function for a moment. This is something that you really ought to incorporate whenever you can with these optimization problems. And you'd be allowed to for this one as well as with the last one we did. And as you're looking at the graph of that area function, you're going to see pretty clearly that it has a minimum value at a critical value. It's not going to be at one of the endpoints. The smallest x could be would be pretty close to 0. The largest x could be, well, I mean, that's somewhere around 4 or 5 maybe. But at any rate, it's at the critical value where the minimum area is going to occur. So we really only have to plug in 1.88 into the area function to find out what the minimum area is. Though that's not what the problem asked. What the problem asked is what are the dimensions of the square and the rectangle, or sorry, of the triangle and the square that would produce that minimum total area. Alright? Now you've already figured out for the triangle, whose sides were each x, that the size of the triangle would be about 1.88, and there were no units given, so we'll leave it at that. Then for the square, you use the fact that y was equal to 2.5 minus 0.75x to figure out that the side lengths of the square were about 1.09. Alright, now a little bit of checking your work here that's pretty simple to do for this one. Since there were 3 sides of the triangle and there are 4 sides of the square, if you multiply 4 times 3, because that was the triangle, times 1.88, and then you multiply 1.09 times 4 and then add those together, you're going to find out that you do get 10. Alright, that will add up to the total perimeter of the two figures. And of course you could use your area function that we had right here. I've got the fractional version. But you can use your area function to determine what that actual minimum area was. Alright, not that bad, these optimization problems. I hope you've got a pretty good foundation on those and that you do well with the examples that I'm asking you to do. Alright, the last thing you got to do is prepare for a Chapter 7 test for me. It won't be easy, but you'll have a couple days in class to study for that. And so I hope that it goes well.